the ride and 2 people at the bottom. The person on top had a ball and a stopwatch. When he dropped the ball, he restarted the stopwatch and stopped the stopwatch when the ball reached the ground. The people on the bottom had a notepad and a phone, which they used to record the video and the times. We repeated this task 5 times to get an average result, which we found to be 2.01 seconds.
So we used the equation D equals VOT plus half AT squared. We knew that VO equals 0 because the ball is being dropped. We found time by averaging the 5 different times we found, and we knew acceleration was negative 9.8. So we found time to be 2.01 seconds, and when we substituted the values, we solved the equation and got distance of the family raft ride to be 20 meters.
We had to both predict the amount of time it would take us to travel around the lazy river 15 times and then find the amount of time to travel in actuality. To do the prediction, we used 3 different methods. First off, we timed the speed of a leaf going 3 meters down the lazy river, and then the second method we used was to time a raft going the same 3 meters. And then thirdly, both me and Dee went around the lazy river once. We took the average of both of our times, and then we multiplied that by 15 to get the third prediction.
In actuality, our measurements came out incorrect when it came for the leaf and the raft. The predictions that we made were totally off. They predicted that we would spend 8 hours on the lazy river itself. But our predictions for the average when we actually rode the raft once and multiplied it by 15 was correct to what our calculations proved.
We think that the first 2, the leaf and the empty raft predictions, were incorrect because the jets of the lazy river are positioned at the bottom. Therefore, the speed of the water at the bottom would be faster than at the top of the river, which is where the very light leaf and rafts would be traveling at. When we actually sit in the raft, we are going deeper into the lazy river and therefore traveling faster. Also, it could have been a slower spot in the river, as we noticed when we were going around that the speed fluctuated at different points.
We had to measure the volume of the oasis pool. To do this, we divided it into different shapes, of which rectangular prisms, trapezoidal prisms, and elliptic cylinders. We labeled the rectangular prisms using letters A, B, C, and D, of which A, C, and D were the stairs, and B was the big rectangular prism in the middle of the oasis pool. The trapezoidal prisms as well as the elliptic cylinders were labeled using numbers, 1 and 5 for 2 of the trapezoidal prisms, and 2, 3, and 4 for the elliptic cylinders. To measure the volume of the stairs, we took the height of each stair and subtracted it from the depth of the pool, allowing us to get the volume of water above each stair vertically. And since the measurements for each of the stairs was about the same for all 3 of them, we used an estimate for 1 stair and multiplied it by 3 to get the volume of all of them. After measuring the volume of the elliptic cylinders as well as the trapezoidal prisms, we added them all together to get a total of about 230 meters cubed for the entire oasis pool. When it came to the precision of our measurements, we believe there were some flaws. For example, when it came to measuring the length for the trapezoidal prisms, there were corners that were curved, which made it hard for us to give exact values for each. As well, the measuring tape was only about 7.5 meters long, and for some of the distances which were longer than that, we had to estimate the remainder, and that's it.